In this video, we're going to take a look at how to differentiate a parametric curve. So previously, we gave a rather concise definition of a parametric curve, but our real goal is to be able to do calculus with these curves. And when you think about what you've done, kind of big picture in your study of calculus so far, probably the first big process was finding the derivative of a curve, right? A differentiable curve. So that's what we're going to take a look at is suppose we had something like x equals f of t and y equals, let's say, g of t. And then we have some range for our parameter t. Let's just say t goes from a to b. And let's say we have a nice smooth curve. Again, so f and g could be any of the functions that we know. And we've seen that equations like this and inequalities like this, they define a curve. So I'm just going to sketch a generic curve over here. Let's say this is our parametric curve. And it looks like that. And, let's say we pick a point. So let's say we pick a point and let's just call that P. And we want to know what is the slope of this parametric curve at this point, right? So if we were to, try to sketch the equation of the tangent line, I'll just try to give a brief sketch here. We want to know what is the slope, right? So that's the question that we're going to try to answer here. And then a little bit more, right? So we want to know what the slope is. Well, if this equation, right, is given in the form y equals f of x, we know we have our rules, right? Depending on what f is, we can find our derivative dy dx, which will also be, or could be denoted f prime of x. And then we would, if we knew the value of x, for instance, at this point P, then we could plug it into our derivative, and then that would give us the slope. So this is what the problem comes down to. Given two separate equations now, one for x and one for y, can we still come up with a formula for dy dx? And it turns out just if we kind of rethink our chain rule all the way back, if you can remember the first version of the chain rule, we can apply it to these two equations, right? Because if you remember, that first version of the chain rule actually comes from two separate equations, and we kind of put them together. So for instance, here we're going to make the assumption that f and g are both differentiable, right? So when you look at this equation, I could write down the derivative of x with respect to t, and that would just be f prime of t. And similarly, I could write down the derivative of y with respect to t, and then that would just be g prime of t. Now, out of these two equations, we want to get an equation for dy dx. The big difference in the parametric case is that our dy dx is not going to be a function of x. It's going to be a function of t, our parameter. And as long as we know the value of t that produces this point P, we can plug that in and voila, we got our slope. So how do we get dy dx out of this? So dy dx. Oh, started to write t. Say dy dx. Well, suppose we just, and again, we have to, we can treat this as if it's a fraction, but theoretically it's not a fraction, right? Because the dy and the dx are differentials, and if we kind of get bogged down in those details, they're very important details, but not for this level of calculus. So if I were to take this expression and treat it as a fraction, and then let's say I divided the top. Let's say I divided the numerator, right, by dt, then I would have to divide the denominator also by dt. right? And you might say, well, why am I doing this? Because, I mean, look at the line just above. We have expressions that have dx dt and dy dt. So if we can somehow introduce both of those expressions into our quote unquote fraction, then it looks like we might have a way of finding dy dx. So let's actually write that down more clearly. So I'm going to write the numerator as dy dt, and then the denominator as dx dt. And it looks like that's all we have to do. It looks like all we have to do is take the derivative of the y equation with respect to t and divide it by the derivative of the x equation with respect to t, and that will give us dy dx. And that's exactly how you find the equation of a parametric curve. So is that it? Well, pretty much, except we just have to add this little disclaimer saying that we got to make sure that the derivative of x with respect to t is not equal to 0, because then we run into that age-old problem of division by 0. So we have to add a little condition here to say provided dx dt is not equal to 0. And there we go. That's our kind of parametric formula for finding the derivative of y with respect to x. And then this now is what will give us our slope of our curve. So let's do an example just to illustrate this. And not only will we find the slope, but let's say we go ahead and find, I don't know, like the equation of a tangent line. So, so let's write up a little question here. So let's see, be the curve defined by, and I'm going to write down our equations here. So let's say x is equal to the square root of 1 plus t. And then let's say y is equal to, let's say 1 over t plus 2. And then let's say this is for t greater than or equal to 0, but less than or equal to 4. All right, so that's our parametric curve. So what are we going to do first? Well, let's find the derivative of this curve, right? Essentially our derivative function, the function that would give us the slope at any point at which the curve is differentiable. So let's find, so first here's what we're going to do. We're going to find dy dx, all right? And basically it's an exercise in derivatives and then applying this particular formula here, which is just another version of our chain rule. And I want you to kind of think about that. All right, so let's find dx dt. So to differentiate the x equation with respect to t, I'm going to rewrite that square root as the quantity 1 plus t to the 1/2. And I'm just going to put dx dt right over here. And then for this, we're going to use our chain rule. So we're going to have 1/2 times the quantity 1 plus t. And then we subtract 1. So that gives us an exponent of negative 1/2. And then technically, I'm supposed to multiply by the derivative of the inner. But in this case, the derivative of the inner is 1. And then we end up having this. Let's just kind of rewrite this in a somewhat simpler form, I guess, a form that's easier on the eyes. So we'll have a 2 in the denominator, and we'll also have the same radical, because now that negative 1/2 exponent is equivalent to 1 over the square root of the quantity 1 plus t. All right, so that's dx dt. Let's do the same for dy or with the y equation to come up with dy dt. So our y equation is 1 over t plus 2. Now here you have a choice, right? You could leave it in this form, or you could write it in a form that's very similar to the x equation by using a property of exponents, right? Now, let me just say this. If you leave it in the form 1 over the quantity t plus 2, then you could certainly apply your quotient rule, right? If you rewrite it like this, the quantity t plus 2 to the negative 1, that's what it is, right? Then you can apply the same rule that we did up here. So let's go ahead and use this version, the quantity t plus 2 to the negative 1, and then find dy dt using our chain rule. So let's bring down our negative 1, and then so times, and then we have the quantity t plus 2, and then subtract 1, so our exponent is now negative 2. And again, we're supposed to multiply by the derivative of the inner. I'm just going to make it clear that I know that I'm using my chain rule, but multiplying by 1 isn't going to change anything. So when we rewrite this, using, again, similar properties of exponents, we're not going to get a root because this is not a fractional exponent, but we'll have negative 1 over the quantity t plus 2 to the positive 2. All right. So here we go. So here is dy dx. So dy dx is where you take the y derivative, which is negative 1. I'm going to write it like this, over the quantity t plus 2 squared divided by the x derivative. So this is our x derivative, so it's 1 over, again, 2 root. Notice I'm using parentheses here just to make sure that I'm showing that I'm dividing by the entire quantity, the 2 root 1 plus t, like that. And then let's see if we can simplify this and just get a nice fraction. So so we'll have a negative in front, right? This here, when I divide by this fraction, I have to multiply by its reciprocal, right? In fact, maybe I shouldn't skip this step. So if we do, here's the negative sign, and then I'll have 1 over t plus 2 squared, and then divided by what I have here, 1 over 2 root the quantity 1 plus t. So here I'm dividing by this fraction, so I have to multiply by its reciprocal. And then maybe I'll go down a little bit now. So then negative 1 over t plus 2 squared times 2 times root 1 plus t over 1. And then I think you'll see now how the fraction comes together. So we'll have a negative in front. We'll have 2 root 1 plus t in the numerator. And then in the denominator, we'll have the quantity t plus 2 squared, right? So that's now our equation for dy dt. All right. So then, what could we use this for? So now that we have our derivative, what could, let's say, part 2 of this example be? Well, we can find the slope at any particular point, right? So let's find, that looks like an m rather than an n. So let's find dy dx, right, evaluated, let's say at t equals 3. Let's say at t equals 3. So once you do that, then we can take our derivative function and then plug in this case, not an x, right? We don't even know what x is at this point, but this value for our parameter. So, which is another way of saying, let me write it this way, the slope of the tangent to this curve at t equals 3 is, and then let's write down the expression. So we have negative 2 times the square root of the quantity, and then I'll just plug stuff in. So 1 plus 3 there, and then we'll have 3 plus 2 there, and then that's squared. So that's equal to negative 2 times the square root of 4 is 2. And then over 5 squared, that's 25. So we end up with negative 4 over 25, right? So again, what this negative derivative tells me that at this value of t, our curve, which we have no idea what it looks like, is decreasing at a rate of 4 units of y per, 4 over 25 units of y per unit of x, right? And remember, our slope is still dy dx, but now it's determined by the value of t. All right, one last thing that we could do here is, what is the equation? So now that we know the slope of the tangent line, what is the equation of the tangent line at that same point? So at t equals 3, right? Well, we know the slope, so we need we would need an ordered pair that the curve passes through. So when t is equal to 3, x, now we would go back to the original x equation. So look at this equation. Use that to figure out the x coordinate. So that's equal to the square root of 1 plus 3. So that's the square root of 4. So that's 2. So that's the x coordinate that the curve passes through when t is equal to 3. And then let's find the y coordinate. So we would use the y equation. So we would use that equation. Again, pretty simple equation. Just plug 3 in right there. So you'd have 1 over 3 plus 2. So that's 1/5. So what this tells me is that, so kind of putting it all together. So this parametric curve, when t is equal to 3, passes through the ordered pair 2, 1/5 with a slope of -4 over 25. And then we can write down, let's say we use our point slope equation for the tangent line. So remember, that's y minus the y value is equal to your slope times the quantity x minus the x value. And I mean, there we go. I mean, that's the equation. If you wanted to kind of simplify it or put it maybe in the slope-intercept form, you could distribute the -4 over 25 and then add 1/5. I'm going to do that all in one step. So we'll have -4 over 25x plus 8 over 25 plus 1/5. Now, just so that I can add the fractions together, I'm going to write 1/5 as 5 over 25. So here's our simplified equation for the tangent line. -4 over 25 times x plus 13 over 25. And notice, even though we're dealing with the parametric curves, right, which are defined in terms of t, we can get the equation of our tangent line pretty easily in the standard form, the explicit form, in terms of y and x. So we don't need, I mean, we could, there's some stuff you could do to write this equation parametrically, not really hard, but this is our more familiar form for the equation of the tangent. All right. So one last thing I want to end with is, suppose we wanted now not just the slope, but let's say we wanted to know if this parametric curve was concave up or concave down, right? How would you do that? In other words, how could you find like a second derivative? And then maybe, you know, what if you want, how could you find a third derivative? So how could you differentiate the parametric curve repeatedly to get the higher order derivatives, right? Well, let's kind of think about the process here, right? So let me write our formula down. So dy dx is, you would take the your y. So basically, what you're doing is you're taking this. You're taking the derivative of y with respect to t, right? And then you divide it by dx dt. So that's just another way of writing it down, right? So it's basically saying, to find the first derivative of your parametric curve, take the first derivative of your, or let's just say the derivative of your y equation, and differentiate it by the derivative of your, or divide it by the derivative of your x equation. So if we were to follow this pattern, let's say we wanted to find the second derivative. it seems like what we would do, because remember, in principle, if you have your first derivative that's in terms of x, and you want to find the second derivative in terms of x, then you just differentiate the first derivative. So maybe that's what we need to do, but we have to now adjust for the fact that our derivatives are now in terms of t, not in terms of x. So this would be, this tells me that I'd have to take the derivative of the first derivative. So replace y with like maybe y prime, or maybe even dy dt. Here we go. But then again, because we want our derivative, or because this is going to be in terms of t, we also have to divide by dx dt. Right? And let me just write down one more expression. Let's say we wanted to find the third derivative of y with respect to x. Then the pattern would be take the derivative of the previous derivative, which would be your second derivative, and again, divide it by dx dt. And I'll just say, and so on, provided dx dt is not equal to 0. All right. But yeah, so that's kind of the way you would apply this process repeatedly. You take the derivative of your previous derivative, right? Everything is in terms of t, and then just divide it by dx dt. Let's do one quick example here to wrap this up, and I'm going to pick equations that are fairly easy to differentiate, so we don't spend time getting bogged down into crazy derivative rules, but just illustrating this process of now finding higher order derivatives for your parametric curve. So let's say we have x equals, let's say t to the fourth, and let's say y is equal to e to the, let's say negative 2t. And for these, t can range from negative to positive infinity, right? So t can be any real number. These will work fine. Okay, so let's go through, and I'm gonna write down, so dx dt, so dx dt is 4t cubed, and then dy dt is negative 2e to the negative 2t. So from this, let's write down the first derivative, right? So dy dx is the y derivative divided by the x derivative, so 4t cubed, and then we can see that we can sort of reduce this, and then we will end up getting negative 1/2, and then I'll say, let's write it like this, t to the negative 3 times e to the negative 2t. All right, so that's our first derivative. Let's find our second derivative now and see how this would work. So we have to take the derivative of our first derivative and then divide it by dx dt. So again, we're going to set up this fraction. So let's do that. Let's find the derivative of this separately and then write down what the expression for the second derivative is. So let's take the derivative of what we have there, the negative 1/2 t to the negative 3 times e to the negative 2. And for this, I'm going to use our product rule, and for the product rule, I'm going to identify this as one function. You can call it your f, and I'm going to identify this as your g. So let me say that if we call that as your g, and then that as your f, then let's apply our product rule. So the derivative of f is, let's use our power rule and bring down the negative 3. So it's 3/2t to the, subtract 1 from the negative 3, that gives me negative 4. And then the product rule says times the second. So I'm just going to multiply it by that exponential. And then add the first, which is negative 1/2 t to the negative 3. And then times the derivative of our second or g function, and that's negative 2 e to the negative 2t, right? And when you sort of look at this, there's not much. I mean, there's some stuff you could factor out, and there's a little bit of simplification you could do. I'm not going to be worried about the negative exponents here. I'm just going to write this term down. So 3/2 t to the negative 4 e to the negative 2t. And then look, we have these two negatives here. And so that's going to make the product positive. And then the 1/2 and the 2, that will multiply to 1. So the coefficient is a positive 1. And then t to the negative 3. And then e to the negative 2t. So there you go. That's the derivative of the first derivative. But now, if I want to find our second derivative like this, I have to take what I have here and divide it again by dx dt. So it looks like this. I'm just going to write this down, and that will be it. If you want to take some time and try to simplify it, have fun. Right? Who doesn't have fun simplifying crazy algebraic expressions with power functions and exponential functions? So we have our dy, the derivative of dy dx. So we just wrote this part down. Make it clear. So we just wrote that part down. And now we're going to divide it by what we had earlier as dx dt, which is the 4t cubed. And when you kind of look at this expression, even when you look back at the first derivative, you realize that this will work, like this will work for all values of t except t equals 0. So to wrap things up, I'm just going to put our little disclaimer and say, hey, you can use this whenever t is not equal to 0. It will tell you if your curve is increasing or decreasing at that point. And you can use this similarly when when t is not equal to 0. And remember what your second derivative tells you? It tells you if the graph is concave up or concave down. So there you go. So now you know how to differentiate parametric curves. Not really difficult. It's just kind of extending the idea of the derivative, and it's based on our chain rule. All right, so I'll look forward to seeing you in the next video where we look at how to do a few more calculus things with parametric curves, and I'll give you a hint. It has to do with area. Right? So, and when you think about area, what do you think about? Integrals. All right, so I'll see you in the next video.